Okay, so hold on a second. Uh, I want to discuss something interesting today. This is something one of my basically videos on higher dimensions of space. So basically, we talk about the fourth dimension. We can, like we talk about spaces or volumes, and then we talk about hypervolumes being the fourth dimension, things like that. But today I want to talk about a lot of people discuss the fourth dimension. So we know, first of all, I want to define dimension to you. If we talk about basically higher and higher dimensions, we talk about increasing dimension. We're talking about, first of all, we have zero dimensions at some location at some point, right? We talk about a point, that being zero dimensions. But the definition of dimension, or the definition of basically growing dimensions, we talk about from 1 to 2 to 3, there are fractal dimensions, there are all kinds of ways to look at dimension, okay? But when we're talking about dimension, say, hello, that's me right there. Okay, so when we're talking about dimension, we're talking about if we have some line, some vector, okay? We have some line, it has some component of a vector. And we draw another line, we say that a dimension, if we increase, let's say we have, this is the way to put it kind of in a basic sense, we take some in dimension. So let's say we have a definition of in dimensions. We say if there is some value n, which is an n dimension, okay, we talk about n representing the dimension, then there is some n plus 1, okay, dimension that is orthogonal to n, okay, and that's basically how I want to define dimension, just to get started with. I want to be able to define dimension. So that is actually what we call a dimension. It's when we have some n dimension. So let's say 0, let's say the point, that's 0 dimensions. Okay, we don't have a dimension, but it's 0 dimensions because there is no dimension. But we say we give it, let's say n plus 1 is orthogonal to that point. So no matter what way we draw the line outside of this point, this marker's not very bold. Hold on a second. Let's say we have a big point. Let's just talk about this point here. And all the way around, almost as if we draw like radii of a circle, we can draw lines that are orthogonal to that point. Okay? So that means, but just for convention, we're just going to draw a straight line horizontally from that point. Just like so. Just like that with arrows. And this is what we call a line. It's just a line. It extends in both directions forever. But this is one dimension. Now look, 0 dimension was the point. Okay, just to get a basic definition so you understand what I mean by dimensions of space. We have 0 dimensions. There is no dimension. There is no... This is not a natural number. It is a natural number according to... It's technically, in set theory, not. It is a natural... It's not a natural number because in set theory it's not. But we're just going to talk about... Let's say 0. We just say there is no value to it. Okay? It is not a natural number. It's basically a neutral integer. Okay? So we talk about 0 value. So we want to say that we give this a dimension that's n plus 1 is 1. And look, n plus 1 is orthogonal to n when n is equal to 0. Because n plus 1 bisects that point. It's kind of stupid to use the word term bisect, but it intersects the point. But it comes out from the point and it is orthogonal to it. And of course, in the case of the zeroth dimension, any line drawn from it can be considered orthogonal to that point because that point has no dimension. Okay? But let's say we call n 1 now. Okay? Let's say we call n 1. Okay? We give n the value of 1. Now, n plus 1 has to be 2. So n plus 1 must be orthogonal to n. And the only way we can do that is to make sure that the line drawn from intersecting this axis, or this line, is 90 degrees from that line. Okay? So if n is 0, after n plus 1 dimensions, every n plus k dimension where k is 1 or greater, or where k is greater than 2, okay, they have to be orthogonal to each other. And anything orthogonal is obviously perpendicular, okay, to the other space. Okay. Now this, let me make this clear. This only is when we're considering a spatial dimension. We'll talk about non-spatial dimensions. When we get up into the fourth dimension, we can't draw orthogonality, really, because we can't draw anything perpendicular to three-dimensional space since we live within the third dimension. Now, a lot of times there'll be a misconception, oh, well, no, we live in the fourth dimension, but we do not. We are spatially three-dimensional. The fourth dimension, we do not perceive the fourth dimension, and I just want to make that clear. We are actually third dimension, living in a fourth dimensional, I guess, universe, I guess is what you say. We live in a spatial dimension, but our space moves around in the elapsing of time. So we are in a fourth dimensional universe if you have time involved, but we are still three-dimensional. And my little brother Cody actually made that point clear to me. He was actually discussing that, and he said, "No, Ryan, we're actually spatially three dimensions." And Cody is right. We always say, "Oh, we live in a fourth dimensional world because there's time," but no, we are still three dimensional. We are spatially three dimensional. And Cody was saying the time dimension is the fourth dimension, but we are still basically spatially three dimensional. So we are looking from the third dimension at the fourth dimension, but we can't perceive the fourth dimension, is what he's trying to say. We live inside the fourth dimension. I mean, we live inside, according to string theory and everything, we live inside 12 dimensions, the 12th collapses, all of that. You could go through all of that, but what we're just trying to say is that we can perceive time, and we can conceptualize it visually, but we are still three-dimensional. So we can't spatially draw anything orthogonal to the third dimension to make a fourth dimension, so we have to be abstract about it, okay? So what I'm going to try to do here is, this is the second dimension. This is a y, we can call this x and y. These are x and y axes, and they are orthogonal to each other. So we have created like a vector space, kind of, and it has a dimension of 2. So this is basically, in terms of vector spaces, if you've taken linear algebra, this is a vector space. This is what we call R2. It's a R2. It is a vector space, and it is 2 dimensions. Its dimension is 2. Okay, and we can have bases, and we can do everything. It is orthogonal. So we have x is orthogonal to y. Now, if we put our pin on the point, and we come up like this. Okay, we can draw a z-axis on the board, but we'd have to bend the axes and things to make it look that way. But in reality, if we come out from the board, this axis that I'm drawing away from the board, that is the z-axis. We call that z. But just for now, we're just gonna kind of rotate the axes of x and y and just draw the z-axis on the board. Now, this isn't actually in a 2D space orthogonality, but we're just kind of bending everything so we can see the z-axis. But assume there are 90 degrees between all 3 axes, okay? So that is a z-axis. That is a spatial third dimension. We have n equals 2, okay? N equals 2, and therefore n plus 1 must be orthogonal to n, just like we've talked about before. So we have orthogonal, perpendicular to n, so n plus 1 is orthogonal to n. So that means 2 plus 1 is orthogonal to the first dimension, 1D. So the third dimension is orthogonal to the second dimension, okay? So this z-axis comes out 90 degrees from the other 2 axes. The 2 axes are also 90 degrees apart, okay? So we have another vector space, R3. This is an R3 vector space right here, R3 vector space. So we are talking about the third dimension, okay? Now, even those who are not mathematical are familiar with dimensions 1, 2, and 3. We know that the dimensions 1, 2, and 3 exist in time, okay? Now you can have infinite spatial dimensions. Now when we talk about our universe, we're not talking about, a lot of people think like, well, okay, how can there be an infinite number of dimensions? Well, in our universe there are not. But mathematically, if there were no restraints on the laws of physics, yes, anything's possible. You could have an infinite number of dimensions. Let's call them spatial. Let's call them temporal. Let's call them whatever. Okay? So we do have infinite number of dimensions. All you have to do is keep drawing lines that represent abstractly those dimensions, orthogonal from each other. And as long as you have orthogonality, every time you draw a new line, if you could, in a spatial sense, you would have a spatial dimension. And technically you can. You can draw the z-axis, and you can hypothetically draw a line outside where this whole space moves orthogonally. So it's almost moving away. It's moving at an orthogonal angle. Or I guess it could be considered 4 dimensions. But in our universe, a lot of physicists define the fourth dimension. We call it fourth dimension. And let's say we call it the W axis. Okay, let's give it the name W. The W axis. Okay? Let's actually call the W axis. We'll call it the W axis, but for convention, let's give it T. It's going to be called T, the time. It's the temporal axis. Because if you take, this is just what I want to show you real quick, real fast. Now, if you take this pin, and let's say this is three-dimensional, but we move it on a line, like on an axis. We move it. It takes a temporal measurement, I guess you have to give a temporal scalar value to say we move the pencil or the marker, right? You can't move the marker without time taking place. There has to be some duration of time. So this is what we call the t-axis. Now the axis can be orthogonal to it, so we can move it in any direction. This acts as almost like we had the point. Okay, it kind of acts in the same kind of way from our perception. We can move it in any direction, and this line it's moving on is what we call the t-axis. We call it the w-axis, but it actually is a temporal axis. Because in our reality, in our universe, we cannot move something without the concept of time. If you read Zeno's paradox, even if time stood still, would it be moving or not? If we shot an arrow across a room onto a target, okay, to the bullseye of the target, would the arrow be moving if time stood still? Well, that has always been a question for mathematicians, but in our modern physics, we realize that if there is no time, there can be no movement, okay? So you have to say that, yes, it is moving, but there has to be some axis of time to say that something is, if you talk about it standing still, it has a rate of movement, but it's not actually a momentum, okay? Physically, in the laws of physics, there is no momentum. Mass times velocity, and there's a time component of that. So there's actually no movement in the object at all, okay? So what we're trying to say with that, so there has to be time. So the fourth dimension, arguably, in the terms of the laws of physics of our universe, has to be temporal in order for something to actually move around or take a pathway. There's like a path it moves on. There has to be an aspect of time, okay, in our universe. Just like on a two-dimensional graph with x and y, for a graph to not stand still, there has to be time. And the third axis acts as a scalar for time, in a sense, unless time is the x-axis, and this is a one-dimensional object, one-dimensional object moving with a second dimension of time. It's one-dimensionally spatial, though, okay? But that doesn't matter. All we're trying to say is that in our universe, yes, you could create a spatial universe where we could have 100 dimensions, 100 spatial dimensions, and in the 101th dimension is its temporal axis. Okay, you could do anything, but in our universe, that's not how we understand our universe, though. Okay, in our universe, if something in the third dimension, does not move, it has no momentum, there is no time aspect. Okay, so we know that. So, in our universe, in the laws of physics, remember I'm talking from the perspective of the laws of the physics of our reality of our universe, okay? Now, this is what we call the w-axis, but we're using t for convention, so we know it's time. What I want to discuss with you is what is our universe's fifth dimension. Now, this is very abstract and very puzzling for a lot of people. What is the fifth dimension? What is it exactly? Now, it took me a lot of time to think about this, but I'm going to tell you what it is, and then I'm going to prove to you why it is, okay? I'm going to prove to you why it is really fast. We're going to end this video probably around 15 to 17 minutes. So, why is the fifth dimension, we're going to say it is a dimension of probability, okay? It is the probability, it's the probabilistic axis. It's the probability axis. It's a probability. So we have basically a temporal axis and orthogonal to it, but let's not look at it like that. Because this is a very abstract space now. So we're talking about t, the time. We're going to actually draw this like this. This little line here is going to be the p-axis, the probability axis, okay? Now the reason this is it's very simple just intuitively. But there's a lot more to it. You have to look at it in a certain kind of way. We know if we bend time, we go back in time. If we bend time, we bend space, we know what happens. we bend, we basically slow time down, right? So then what does that mean? If we have an object moving in this direction, basically in this amount of time, and then we draw, and there's one point on the p-axis, this arrow intersects like that. So it's going to intersect that point. Then there's a point up here on the p-axis that we have the same spatial, three-dimensional spatial object running through that point. I can't draw this, marker is not wanting to work. So this is spatial running through that point, correct? Well, that's the whole point. There are two instances of time where time is altered, okay, on this axis. And you have to think about it mathematically. It's orthogonal to P. And we want to call P U, but we call it P for convention. That's the U axis, because we have, X, Y, Z, W, U. That's okay. We'll call P, but it's equal to U. The P is the P axis. We'll call that P for convention, but it is our U axis. This is a basically a fifth dimensional construct. This is a fifth dimension, because it is a fifth dimensional orthogonal. If n equals 4, then n plus 4 is obviously 5. And we know n plus 1 is orthogonal to n of n dimensions. So, we know there is an orthogonality. I draw it like this. Yes, it doesn't spatially look orthogonal. It looks like a curve, but it doesn't matter. We're defining it mathematically as orthogonal, but it's outside. It's a reality we can't perceive spatially, so we have to look at it like this. But just so I show you, it could be a straight line, whatever you want to call it. It could be any line. But anyway, we intersect this point at 90 degrees in each of these points on the curve. That means this object is moving in different directions on a different axis of time. So it's basically saying that this object could move straight out, or it could move at a different angle, or any rotation or move around, or wherever it wants to go, right? But there is an axis, we'll call it a scalar of probability, that is saying that every point on the probability axis are different instances of time. So we're saying that things could have happened simultaneously in time. Okay, so we have like different axes of time at 2 seconds, at the 2-second mark. We're on a different place on the probability axis, and there are infinite number of points. That's just saying the infinite number of probabilities of an object moving around in a different orientation or in a different way on different points on the p-axis. So as we draw lines through all these points, we say that this is our probability axis, because we have the object moving or orienting itself on different times, or different. It's dependent on different vectors of time, or whatever you want to call it. It's dependent on different how do you say it? It's dependent on different axes of time. So basically, we have one point in time. There's different instances because it is acting in different ways. So it basically, there's like a infinite number of 2-second marks. But at that point, 2 seconds, this object is oriented in a variety of different ways. But in our universe, this pin, for example, this pin can move back and forth. But let's say it takes 1, 2, 3, and at the same time, in some other instance of time where we have a different space and time, we have 1, 2, 3, 1, 2, 3, and all these different instances are points on the probability axis. So time is moving like outward, probability is moving like a curve, but it is intersecting these outward time movements. So we have 1, 2, 3, that's one movement on one point of the p-axis. This orientation is the same, we're in the same instance of time, we're still on that same 2-second mark, but it's taking different positions in space at the same point in time. So it's almost as if we have different universes with a pin, a marker like this, and it basically begins to break apart into a bunch of different markers, moving in different ways. So we're basically, these markers are basically, breaking off from each other and moving in their own kind of orientation at the same points in time. But we only see one marker moving around. But if there was a different probability or a different instance where it would have moved in a different way, that would have been another point on the probability where time intersected it. So we have to look at it like this. If it intersected at this point, this pin made some kind of motion in a given amount of time. If we look at it down here, it made different kinds of movements in the same points, at the same points in time as this one did. It's just in a different universe. So we're actually looking at the fifth dimension as being probabilistic outcomes at the same points in time. So I could have, an infinite number of movements or an infinite number of outcomes of what the marker, how the marker moves or how it orients itself. And we record that instance, and then there's another way it can move in another point in time and intersect a different point on the p-axis, because that one intersection point is just a given point on the time axis at which an event occurs with the marker. So the marker is basically moving itself, and basically there's, like I said, each point represents another marker, and it's the same marker but in a different reality or a different universe that's moving in a different way. So it's the probabilities at which this marker can move in different ways. So we have proven now intuitively that the p-axis, or this fifth dimensional axis, is orthogonal to time. Okay, so every space in between, if we took the area under some curve in this space, we'd say that the sum of those areas, or those rectangles, we're trying to sum up some area under the curve, we'd see that if we have some velocity taking place, it's basically a number of velocities. It's a number of velocities taking place. And it's just interesting to think about it like that. So there's like a bunch of different schisms in time, because we understand that the z-axis has one length. So there's some magnitude to the z-axis, but in different directions, hitting the p-axis at different points. So we know that this is the same temporal magnitude, but we're intersecting the p-axis at different places, meaning each one of those little lines intersecting the p-axis is obviously a different probability. It's a different outcome of a universe. It's a different universe is born, and something is acting in a different way in that amount of time. Because the time is the same. We have 1, 2, 3, and 4 seconds, but the pin is doing different things in that amount of time. And each one of those different things the pin is doing, those different actions the pin is taking, in each probability is what each time it intersects the p-axis. So that is what the fifth dimension is, and I just think that's just kind of a fascinating way to look at 5 dimensions. Now, 6 and 7, now this is only theoretical, especially when you get up to 6, 7, 8, 9 dimensions. This is all string theory, and it starts becoming real complicated. But at least I have a good hold on how to intuitively explain how the fifth dimension works in a universe, in the universe like we live in. So it's kind of like, in the laws of physics, that is how our universe works on 5 dimensions. It has a temporal dimension, and then it has a probabilistic dimension, where we have different outcomes of some movement, some momentum, with a given amount of time. Thank you.